Hi class, this video is on topic E2, properties of sound. Just to recap, there are two different types of mechanical waves: transverse waves, where the particles vibrate 90 degrees to the flow of energy or the direction of the wave. So you can see that it appears, especially if you trace this top edge, it appears as if the crests are moving to the right. Well, the crests are moving to the right. It appears as if the particles are moving to the right, but when you focus on individual particles, you can see the particles are moving up and down, and the wave is moving left to right. So that 90 degrees is what characterizes a transverse wave. Longitudinal wave, particles are vibrating parallel to the direction of the flow of energy. So the wave is traveling from the left to the right because it appears as if particles are moving to the right. The crest or the compression, we would say crest in the case of a transverse and compression in the case of a longitudinal, looks as if the compression is moving to the right. The particles are just vibrating left, right, and they're oscillating in a small range within its place. So longitudinal is when the motion of the particles is parallel to the wave direction. Transverse is 90 degrees. With the longitudinal wave, they're a little bit tricky to draw. If we were to try to draw them, we would want to show compressions, areas of higher pressure, and rarefactions, areas of lower pressure. So the particles are more bunched up here, particles have more space here. And the distance between a compression and the next compression, or rarefaction and the next rarefaction, is called one wavelength. Because longitudinal waves, it's possible to draw them, but they are not as easy or simple to draw as transverse waves. Even though we know sound is a longitudinal wave, we tend to look more at the transverse waves. So here, in addition to having the equivalent of a compression, which is a crest or a maximum, and the equivalent of the rarefaction, the trough, we can also more clearly see something called phase shift and amplitude. And we can also see wavelength. So amplitude is important in sound because it is the volume, so the loudness of the sound, or the amount of energy. So it's really important to be able to visualize amplitude. Amplitude is the maximum displacement of a vibrating particle from its equilibrium point. Wavelength, we will talk in a moment about how wavelength indirectly determines how high-pitched or low-pitched the sound is. So wavelength and amplitude are maybe arguably the most important geometric characteristics when we're talking about sound. There's also the time-based characteristics of sound. We have period, which is the time for one cycle, or frequency, which is the number of cycles for one unit of time. The number of cycles for one unit of time will indicate how high-pitched or low-pitched, or the tone of the musical note. So the sound being very high-pitched would have a very high frequency. So in 1 second, there would be many crest troughs. But for a low note, they would be, we would have fewer, so they would appear to be more spaced out. So frequency gives you the pitch of the sound. And that's an important time-based characteristic when we're talking about sound. Wave speed is something that incorporates a geometric aspect and a time-based aspect. So wave speed puts the two together, and it's frequency times wavelength, or lambda. And we have talked a little bit in that first lesson about how the wave speed depends on what the wave is traveling in. So if you have a solid, liquid, or gas, the wave speed will be different. And if you have within a liquid, if it's a warm liquid or a cold liquid, we're going to get different wave speeds. So wave speed is a property of the medium. And frequency depends on the wave source. So it actually depends on where the wave is coming from. So with sound, that would be from the speaker. And these are important to keep in mind as we are going to be using this equation throughout this unit. Okay, so now fully, what is sound? The definition is a form of energy produced by a rapidly vibrating object causing a longitudinal wave, which is detectable by sensory organs such as the ear. So it is a longitudinal wave, and if the wave has particular properties, we can detect it with our ear, and that makes it sound. If you take a look at the tuning fork, which I briefly mentioned in the first video of this unit, in a tuning fork, it would be hit, and the prongs of the tuning fork get closer and farther apart. And as they do that, it changes the pressure of the air around the prongs. So it sends out these pulses of compression, rarefaction, compression, rarefaction. So alternating areas of high pressure and low pressure. And then eventually this wave reaches your ear, and your ear drum is going to go in when there is an air compression and out when there is rarefaction. And the number of times that your ear drum goes in and out gives you the pitch of the sound, and how much your eardrum goes in and out would give you the loudness or the intensity of the sound. I'm simplifying a little bit, but that is essentially how it works. Instead of the tuning fork, if we have a drum, as you hit the drum, the membrane goes up and down through the vibration, and that vibration transfers into a sound wave that eventually reaches your ear. We can see that the regions outside of a tuning fork have higher areas of pressure and lower areas of pressure, meaning that there are more particles per unit of volume or less particles. If we look at a speaker, as the cone of the speaker is going out or in, we get high pressure or low pressure. So let's say in the speaker, the cone is moving out, then we get high pressure, and that pulse of high pressure is sent radially throughout the room, in the air in the room. This is like if you have a slinky and you pulse your hand left and then right, it's going to send that compression along the slinky. And then when the cone is pushed back into the base of the speaker, there is a rarefaction, and so there's different categories of sound. There is audible sound, which is 20 hertz to 20,000 hertz. So if you remember that hertz is the unit of measurement for frequency, and frequency is the number of times something happens in a second. So if you have a 20 hertz sound, that means there are 20 crests and troughs in 1 second. Or if we're talking about sound, it's I guess 20 compressions and rarefactions per second. We can have frequency for other things inside. So for example, in the electricity unit, we talked about that an outlet is a 60 hertz alternating current. So that meant that the electrons change direction 60 times per second. So if we get crests and troughs 20 to 20,000 times per second, we will hear it as sound. We'll detect it as sound. If we're a little bit outside of that range, we have either an infrasonic wave or an ultrasonic wave. Infra would be lower than 20 hertz. So if we had something that was vibrating at 5 times per second, that wouldn't be fast enough for us to detect it as sound. And then we have ultrasonic waves. When something is vibrating that is more than 20,000 times per second, then we don't hear it as well, and it's a frequency above the audible range. So this is the audible range, 20 to 20,000. There are various applications of ultrasound. So ultrasound is where the frequency is higher. So high frequency sound waves, they're widely used in medical applications for diagnostics and treatments. They are safer than X-rays because they are less energy, but they are less detailed. So whenever there is an imaging decision, the appropriate imaging technique is selected based on what type of tissue needs to be observed and how much detail is required, and as well how much harm there would be to the tissue. So ultrasonic waves, which are lower frequency and therefore lower energy than X-rays, are used in pregnancy to observe development of the growing baby. So that's an example where it's sort of checking, so in the realm of diagnostics. And it could be used in treatments such as to break up kidney stones, because a wave is a transfer of energy. That energy, if designed correctly, could be, if applied correctly, could be used to do something useful like kidney stones. That energy could be damaging, which is why we always consider what is the safest option for waves. Ultrasound ranging unit of cameras is another application. And recall that universal wave equation, V equals F lambda. We are going to be using this throughout the unit, as I mentioned earlier. But what really is speed of a wave? So if this end sends out a crest, we could measure how much distance is from here to the end, and we could track that crest, press a stopwatch on, and then check how long it takes. So I'm trying my best with the mouse, with the cursor, to trace this crest. And then I would press stop on my stopwatch as soon as it gets to that point. So that distance divided by that time is the wave speed. This wave speed, we said, is a property of the medium. So what the wave is traveling in, whether it's solid, liquid, or gas, its temperature, its density, the medium properties determines the wave speed. So in particular, if we're talking about the speed of sound, we have an equation that relates the temperature of the air to the speed of sound in that air. So most often we're sending sound through air. You can send sound through water or solid, but most often we're talking about projecting sound through air. So temperature of the air gets subbed in here in degrees Celsius. Units will cancel out with this sort of slope value, and the degrees Celsius cancel out, and we have left with a number that gets added to 331 meters per second. So if we have 0 degree air, we are traveling 331 meters in a second, and anything warmer than that would increase the speed. If someone were to shout and it would be a 0 degree day, that means their voice travels 331 meters in a second. Okay, let's talk about the speed of an object as it compares to the speed of sound. So we have something called the sound barrier and sonic booms. Supersonic is when objects travel faster than the speed of sound. And the reason why it's interesting to compare how fast an object is going compared to sound, because if you exceed the speed of sound, then you can hear a sonic boom. So you could see if an airplane is stopped, any noise that is coming out of that airplane, or any vibration, the crests would be evenly spaced out in front of the airplane and behind the airplane and to the sides. But if a plane is moving and the plane sends out a crest and then sort of chases that crest, you can see that the crests bunch up in the direction that the plane is moving. And the crests are more spaced out behind the plane. And if we can approach the speed of sound, that means you're going so fast that you send out the crest, but you've caught up to it immediately. Like you're never letting the crest get away from you. So there is an area of very high pressure here, and it results in a sonic boom. And you might visualize it as like a cone like this because of moisture in the air condensing because of that instant or very fast change in pressure. And when I say you can visualize it, I mean, this is actually a picture. This would actually be seen, observed, depending on, the conditions of the day. And the crack of a whip is because there's acceleration there, and at that point where you hear that crack, there is speed that is faster than the speed of sound, and that's why you hear that crack. It's a little tiny sonic boom. So because we're interested in comparing objects' speeds to the speed of sound, we actually have a ratio that's often reported, and it's called the Mach number. And Ernst Mach was a physicist who decided that we should start looking at this ratio. So M, capital M, is Mach number, and it's equal to the airspeed of the object divided by the local speed of sound. So the numerator is just how fast your plane is going, and the denominator is how fast sound goes in that air at that temperature. That's why we say local speed of sound. And the formal definition, the Mach number is the ratio of the airspeed of an object to the local speed of sound at the same temperature. So let's try an example. Let's say if we have an airplane flying at 1,234 kilometers per hour in air that is -5 degrees Celsius. Determine the Mach number of the aircraft. As you go to a high altitude, we often get colder temperatures. So this is not, doesn't have to be the dead of the winter to necessarily for this question to be relevant. So we're first going to write out our givens. We have the speed of the object, but it's not in SI units. So you'll want to convert that to SI units. So we do that using, actually there's two ways that we can do this. We can convert, so notice that the Mach number is unitless because the units on the top and the bottom are going to cancel. So we don't have to be in SI units. We can be in SI units, but both numerator and the denominator have to be in meters per second if you're going that route. The other option is to calculate the speed of sound in meters per second and then convert it kilometers per hour. So when I wrote this up, I was feeling like leaving the kilometers per hour, I calculated the speed of sound using my new equation, 331 plus 0.6 times -5 degrees. And I get 328. So because I'm colder than 0 degrees, I get a little bit slower sound than 331 meters per second. So that number, not rounded, all of its digits, is going to go into my unit analysis. And I'm going to, so just because it's been maybe a little while since the motion unit, I just want to go over unit analysis quickly. Meters per second, we have meters on the top. So to get rid of meters, we're going to put meters on the bottom. And you want to go 2 kilometers. So you put kilometers on the top. That's not going to cancel out with anything. Meters will cancel out. And then vertically, you're going to say, well, what's equivalent? 1 kilometer equals how many meters, or 1 meter equals how many kilometers? So you're going to write something on the top and the bottom that the values are equivalent. So 1 kilometer is equivalent to 1,000 meters, and we can use the ratio in this way. Then in terms of time, we know that 1 hour is 3,600 seconds, and we want to get rid of seconds. So instead of writing 1 hour over 3,600 seconds, we're going to do 3,600 seconds divided by 1 hour. And you can see the seconds cancel out, and kilometers does not cancel, per hour does not cancel. So we get 1,182 kilometers per hour for our denominator, because that's the local speed of sound in kilometers per hour. And then the numerator is just our given, 1,234 kilometers per hour. Then our Mach number is 1.04. So you're basically traveling at the speed of sound if you round to the correct number of significant figures, which would be 2. So if 5.0 was the question, then you would round to 1.0. If 5.00 was in the question, you would round to 1.04. And just to take a look at different temperatures of air and the speed of sound in that air, And then different substances. So air at 20 degrees, it has a faster speed of sound than sound travels through air at 0 degrees. And that's still faster than if it was air at minus 20 degrees. Glass, we have sound traveling faster. So if you think why to the first video of this lesson, since there's a higher density, the transfer from one particle to the neighboring particle is faster and more efficient. So that's why we get a greater speed of sound. And in general, all the solids in this table, we have sound traveling faster in all of the solids than in gas. And once again, this is a really important, like a big concept, that the speed of a wave depends on the medium and its properties. So our last topic relating to sound of this lesson is intensity and loudness. Loudness describes how humans perceive sound energy and depends on sound intensity. So this is related to the amplitude. The amplitude really tells you how much energy is being transferred. And sound intensity is the amount of energy being transferred per unit area. So sound intensity is a measure of, I guess, power per unit area, but we know power is energy per second. So you can think of this as like a direct energy value, whereas loudness is a different scale about how humans perceive sound. So loudness takes sound intensity and we've converted it to units that are more convenient for our measures. So that might not be, hopefully the next slide is more clear on that. So instead of saying, well, the range of human hearing is 1 times 10 to the minus 12 watts per meter squared to 1 watt per meter squared, there is a new scale called the decibel scale, and it's the sound level. The sound level is measured in decibels to describe the sound intensity in a more convenient way, from 0 to 130 decibels. And each increase in one sound level, one bell, is an order of magnitude increase in sound intensity, so 10 times. So 1 bell is equal to 10 decibels. So when you go from 10 to 20 to 30, that would be an order of magnitude increase. I will do an example. Do not get confused between the threshold of human hearing based on loudness and the range of audible frequencies. So remember that 20 hertz to 20,000 hertz is the frequency that we can hear, and this is the loudness that we can hear. So if we have a sound that is within the right frequency, but just too quiet, so lower than this number, we won't hear it. And then if we increase the volume, we will hear it as long as it's within this range. And then even if a sound is between these two loudness, within this loudness range, it might be the wrong frequency. So maybe if you turn up the frequency to 30,000 crests per cycle, or crests per second, that's a frequency that is too high. That would be ultrasound, and we won't hear that either. So in order to hear sound, it must be within the correct frequency range and the correct threshold, the correct loudness and the correct frequency. So let's explore this, the order of magnitude increasing the sound intensity. So in your textbook, you have a long list of different sounds and the sound intensity and loudness level. So for example, an alarm clock. So you wake up in the morning and your alarm clock is probably about a meter from you. And the alarm clock, the typical alarm clock, is 1 times 10 to the minus 6 watts per meter squared, which is 60 decibels. And then let's say a rock band is 0.1 meter per watts per meter squared, which is 110 decibels. So it's a lot easier, rather than having all these scientific notation numbers, to just use the convenient loudness level, the sound level in decibels, which is why if you have a workplace and they have to set limits for the sound level that is safe for you to be exposed to over a long period of time without hearing damage, it will be given based on decibel values. So if you have a workplace over, I believe it's around 90 decibels, if it's a constant sound in your work environment that is over 90 decibels, I believe, then you have to wear hearing protection and your employer has to provide that for you. So let's take a look at the math comparing a few different sounds. So this threshold of human hearing, the intensity was this number, so we're going to write it down. So we write down that sound intensity, and it's 0 decibels. An alarm clock is 1 times 10 to the minus 6 instead of 1 times 10 to the minus 12. And that's a difference of 0 decibels versus 60 decibels. And every level change, so 60 to 50, 50 to 40, 40 to 30, that's 10 times the amount of sound. So 60 compared to 0, that it would be 10 to the 6 times louder. Now, if we go from alarm clock to a rock band, which is 110 decibels, 60, 70, 80, 90, 100, 110, that is, we've got 50 decibels difference. So because that's 5 of those levels, that would mean it's 10 to the 5 times louder from here to here. And there are some questions for you to consolidate this, this lesson. So please complete these practice questions and submit them on Google Classroom, and also make sure to submit your exit ticket for this video. Have a great day.